Welcome to the third video on Introduction to Quantum Field Theory. This one will talk about vector fields. So we talked about different types of fields last video, and you could have scalar fields like this, and you could have vector fields. You could also have spinor fields, but I didn't draw those for reasons I explained in the last video. But this video we will be fully focused on vector fields. So whereas a scalar field assigns a scalar to each point in spacetime, a vector field assigns a vector to each point in spacetime. And the first thing to note is that a vector has structure, specifically here, internal structure. So in general, a vector has structure, but when we're talking about fields, so a vector has structure, so a vector field has internal structure. And the structure here is its basis. Or it can have structure without the basis, but the basis is what in tensor formalisms traditionally gives its structure. But we know from geometric algebra you don't really need a basis actually to have vector structure. So specifically, it is convenient to write the vector field in the below form, where if this A mu, which relies on the spacetime position x mu, then it can be written as epsilon mu f of x mu. And what this right here, this is polarization. Which effectively is like a basis. So it's the internal structure. And this right here is the field strength. Field strength. Which is usually some wave. And specifically, it's usually e to the I t mu x mu. So this proving this will come later. For now, we're just going to kind of assume a lot of this stuff. The first this part one introduction to quantum field theory set of videos is going to mostly cover the mathematical preliminaries and the conceptual preliminaries, and stuff will be proven later. So it helps to rewrite vector fields in this form, where you have the essentially basis, which acts as a kind of polarization, and then you have the field strength, which this is a scalar function. And then it is conventional to normalize this polarization basis. Now the notation here is going to look a little bit weird, but that's okay. So essentially this basis satisfies the Minkowski metric. If you remember from way back when, the Minkowski metric is this matrix right here. It's either 0 or 1 or -1. But this basis right here satisfies exactly the same thing. But for some reason, the notation for the polarization stuff here is like slightly different where you denote the vector e epsilon mu, but then you have the indices here. I'm not quite sure, but it looks like it's just traditional. So the simplest resulting the simplest set that satisfies this, the simplest resulting vector basis is then and then these are all very similar. Okay, so get these get these as the simplest resulting vector basis. Recall that this right here uh, corresponds to, like, it implies this following set: epsilon naught mu, or forgive me, let me just rewrite this. It's easier to say, but this works because of the Minkowski metric. So epsilon lower script mu is equal to epsilon superscript mu. Or you can write it like this. And there you go. And if you're trying to recall what this relation is telling us, originally it's this right here. It's this relationship right here. Oh, which I can actually, I did make a typo here. This should be new. But yes, this is the same as the thing that I showed up there. So any vector A mu may be written as, so it can be written in this basis. So A mu can be written as A naught which this is just A naught, A1, A2, A3. So while the indices here are changing, on the bottom, they're not covectors. The fact that the mu is up top represents that these are in fact contravariant vectors, and that's why you have contravariant indices out front. So it is important to note that while any vector field A mu can be written, or can be any configure or any mathematical configuration of this quantity here, where this is the breaking up of A mu into a polarization and field strength. Only solutions to equations of motion show what configurations are physically realizable. So essentially speaking, while mathematically you can have kind of any kind of vector field, it can point in any direction, it can look like anything, you can have a general vector. Only solutions to equations of motions will tell you what configurations actually exist physically in the real world, like which configurations of vector fields actually correspond to physical fields that exist. So let's talk a little bit about this and give some examples. So examples of physically realizable, oh no, realizable vector fields. So in general, solutions are waves, which implies, which I mean, I'll just say it this way. This means they oscillate. The solutions, that is, the solutions will oscillate. If an object is then traveling in a specific direction at a constant speed, the vector field doesn't oscillate in that direction, or in that propagation direction. This is a somewhat naive view, but it gives the correct intuition. So, in summary, oscillating in a particular direction implies a changing propagation velocity. Propagation velocity in that direction. Since all objects travel at light speed c in their rest frames, since they all have changing, they're all moving through space-time at light speed in their rest frames, and thus, that's a bad thus, and thus don't have changing propagation speeds, or more appropriately, velocities. The oscillations must be transverse to motion. That's a lot of writing, a lot of words. In general, solutions are waves. This means they oscillate. If an object is then traveling in a specific direction at a constant speed, the vector field doesn't oscillate in that propagation direction. In summary, oscillating in a particular direction implies a changing propagation velocity in that direction. Since all objects travel at light speed in their rest frames, and thus don't have changing propagation velocities, the oscillations must be transverse to motion. So we have two cases here. So if any object has mass, then it has a rest frame. If any object is massless, then there is no rest frame, and every object, or every observer will observe a massless particle traveling at light speed. So then you have basically two cases. You have the massive case, and in the massive case, it's traveling only through time at c at light speed, which corresponds to this basis vector and implies that for a massive field, it is proportional to 1, 0, 0, or sorry, I have that reversed, 0, 1, 1, 1. So this is the massive case. It travels only through time in its rest frame at light speed, which corresponds to the polarization basis vector in the time-like direction, which implies that the magnetic, or sorry, the vector or vector field is proportional only to the space-like directions because it can't have be oscillating in the time direction. So the polarization is completely transverse to its motion through time. Now, then there is also the massless case. So it travels, we're going to just work with one axis. So it travels through time and technically it's any direction, but we're going to just choose the z-axis because it makes it easier to analyze. And this corresponds to the time-like and then the z direction, which implies that the vector field of a massless particle is proportional only to these directions here. So this kind of makes sense. You would have an example of this would be if you have some kind of, maybe let's just call it a negatively charged object, then you would have fields coming out of it like this. And this makes sense because if you have your x, your y, and your z direction, you have something moving at light speed along the z direction, well then it can only propagate to the sides, and so you only get stuff like this. And if this looks familiar to you, then, or it should look familiar to you, because this is basically how electromagnetic waves propagate. And this is how charges influence things. So if it make that should make sense because the electric and magnetic fields are vector fields. And so it turns out that the vector fields that we've always been interested that emanate from point particles or that oscillate and propagate through space, electromagnetic waves, these are just the massive and massless cases of a vector field. And so hopefully this helps with intuition for understanding what a vector field is in quantum field theory.